Welcome back to this channel. So in this video we are going to be handling carboxylic acids. So this video is presented to you by Yusuf, and you're advised to subscribe to the channel and share the video to your friends so that you can all benefit as a family. And this chapter 8 we are going to be looking at carboxylic acids. So carboxylic acids, as we can generally define them, we are going to be saying that these are going to be saturated organic compounds with a general formula of RCOOH. Now we are saying that where R is going to be our alkyl or aryl group. Now we are saying that the functional group in the carboxylic acid is called the carboxyl group, or you can identify it using a formula this. So looking at the nomenclature, we are going to be looking at the naming of the different carboxylic acids that we cover at advanced level. Now we are saying that when you are naming the ending E in alkanes is just going to be replaced with prefix or IC, and we are saying that in the corresponding carboxylic acid, for example, if you're having ethane, ethane means that you have two carbon atoms, so the ending in ethane we replace it with this prefix or IC and it becomes ethanoic. So the functional group here is going to be COOH on each and every carboxylic acid. So this compound, since it has two carbon atoms, is going to be called ethanoic acid. This compound, since it has three carbon atoms, is going to be called propanoic acid. And this compound, since it has a benzene ring and then a carboxyl group, it's going to be called benzoic acid. Now we are saying that any other group on the chain are identified by its nature and position, just like we looked at the naming in other compounds in the previous videos that we have been covering. Now we are saying that numbering starts from the carboxyl group. Just like other videos, numbering starts from the functional group. And you're saying that the position of the carboxyl group is not mentioned since it is always at the end of the chain. So this carboxylic group in every carboxylic acid, it must be at the end of the chain. So its position is not named anywhere. Otherwise, it would not make any sense if you say that one carboxylic acid. So we don't name it. Examples, this one having a benzene ring, what is attached to it, I say that this is a phenyl group, what is attached to it is the ethanoic acid. So we call this one 2-phenyl ethanoic acid. We are saying that this two is showing that the functional group is on the second carbon atom, away from this carbon atom and this carbon atom that are attached to this benzene ring. So you're saying that this is going to be called 2-phenyl ethanoic acid. We start counting from the position that contains the functional group. Now functional group is contained on this carbon atom which we start with. So that means that this is the first carbon atom, this is the second carbon atom, and this phenyl group is attached to the second carbon atom. So that's why we call it 2-phenyl ethanoic acid. Now going to this one, it's going to be called 2-hydroxybutanoic acid. I say that we start counting starting from this side. So this is the first carbon and then this is the second carbon. So that's why it's called 2-hydroxybutanoic acid. I'm not going to review the naming. I hope you are now well conversant with the naming. So this one is going to be called 2-aminobutanoic acid. Now looking at the isomerism in different carboxylic acids, we are saying that carboxylic acids are going to exhibit both chain and functional group isomerism. If you look at the examples under isomerism, for example, you have this question set and we are saying that you are going to be writing the structural formula and the opaque names of all isomers containing a general molecular formula of C3, H6 and O2. So first of all, looking at the solution, we can list out the different isomers. I told you need to make this a daily practice because you never get a paper without such a question. You always calculate for empirical formula and then you calculate for molecular formula, and then the other part will always prompt you to find the different isomers present in that compound. So here I listed out some, and I found that I can have propanoic acid and I can have methyl ethanoate. For as long as there is the same number of carbon atoms, same number of oxygen atoms, and same number of hydrogen atoms. You find different isomers provided they have the same numbers of the atoms that are present in your molecular formula. Now we are saying that notice that the carboxylic acids are going to be isomeric to the esters. So that means that for every carboxylic acid that exists, it's always going to isomerize with an ester. That means that it can either, when you catch it for a molecular formula, it can either be a carboxylic acid or an ester. So how will you differentiate whether it's a carboxylic acid or an ester? Always in the following question, they'll provide a physical property of any carboxylic acid to help you identify what you're looking for. Now you are having here an assignment and you are being prompted to write the structural formula and outpack names of all possible isomers of a compound containing 4 carbon atoms, 8 hydrogen atoms, and 2 oxygen atoms. Synthesis of carboxylic acids, you are going to undergo the following reactions. Now notice that here when you're using oxidizing agents like dichromate and manganate 7, I told you to rearrange this. Hydrogen ion or a proton should be struck with a manganate 7. So rearrange that. So it's going to be manganate 7 ion, which is in aqueous. And then you stroke it with the hydrogen ion. That's the proper appropriate arrangement that is required. So under synthesis, we are saying that you can get carboxylic acid in part A by oxidizing primary alcohols, but this is involved in 2 stages if at all you are using a weak oxidizing agent. And a weak oxidizing agent, we are saying that you can either use dichromate. If you're using dichromate in limited amounts, it's always going to first give you an aldehyde. And then if you use it in excess amounts, it's always going to take you to a carboxylic acid. But notice that here, this is strictly for primary alcohols. So to convert a primary alcohol into a carboxylic acid, in one step, you must use excess acidified dichromate ions. So that's what we're having. The first step, using limited, it gives us an aldehyde. So if it's ethanol, we get ethanol. And from ethanol, we go to ethanoic acid. And all that happens when you're using dichromate 6 ion, which must be in an acidified medium. Now, however, there are some strong oxidizing agents like manganate 7. So manganate 7, for it is one step. When you get a primary alcohol, it oxidizes it straight away to a carboxylic acid. So we are saying that manganate 7, but it must be in acidified medium. I've told you to change the arrangement of this. Manganate 7 first, stroked with the hydrogen ion. So it will give you, so from ethanol you go to ethanoic acid as a straight route. However, you can also use Grignard's reagents or Grignard's compounds. So if you're having a Grignard's compound, first of all, the first reaction, you react it with carbon dioxide in ether, and then later you hydrolyze with acidified water. Then you also be getting propanoic acid here. Now what Grignard's compound does is that it increases the number of carbon atoms. Here we are having 2 carbon atoms, but also this carbon dioxide we are adding, it adds up here. But remember that carbon dioxide contains a carbon atom, so the total carbon atoms in our final compound are going to be 3. And then hydrolyzing with acidified water yields us the acid that we are looking for. So going to part B, we are saying that oxidation of methylbenzene using alkaline potassium manganate followed by dilute hydrochloric acid can also yield us carboxylic acids. Thus, when you're using alkaline manganate 7, I've told you always during this, it's always manganate 7 ion that is supposed to come first, and then the condition or the medium it works in to be brought last. So when you're having alkaline manganate 7 and then you heat, you always get a carboxylate salt. But if you get this carboxylate salt and you hydrolyze it with dilute HCl, you are going to get your benzoic acid. However, there is a direct route to that, which is very common in your synthesis reactions and is very important because it's hardly missed out in any paper that is being said. So that's when you are using acidified potassium manganate 7 or simply acidified potassium manganate 7 ions. So the arrangement is this, but I told you proton comes last, magnet 7 comes first. And then you make sure that they're all in aqueous state, and then you heat. So it will take you from methylbenzene or taurine straight away to benzoic acid. Now note in the following that when you want to convert to any benzoic acid, it's independent of the number of chains which is here. We consider this one, we generalize this one as the R group for as long as we are having a benzene ring attached to the R group, always alkaline, always acidified magnet 7 ions when heated takes you to benzoic acid strictly, independent of the number of carbon atoms present in that compound. So that's why I provided 2 examples here, showing you that even if there were 3 carbon atoms here, when we hydrolyze or when we acidify that compound in acidified manganese 7 ions and we heat, we always end up with benzoic acid. The common mistake that most of you do is saying that you are only replacing 1 carbon atom with our carboxyl group, which is very wrong. What this reaction does is that it eliminates every carbon atom which is present on that compound that is attached to the benzene ring, and then it adds our functional group, which is the carboxyl group. So for whichever the length of the chain which is here, it's always going to take you to benzoic acid. When you're having this compound and you also react it with acidified manganate 7 and you heat, it's also going to give you benzoic acid. But make sure that the states are aqueous in nature. So going to number 2, we are saying that you can also use carboxylic acids from Grignard's reagent. Now we are saying that here, Grignard's reagent is reacted with carbon dioxide, and this is done in presence of ether, and then is followed by acid hydrolysis. And the acid hydrolysis here, we shall be using acidified HCl or dilute HCl. So Grignard's compound here, you react it with carbon dioxide, but this must be a solid or a gas, and then you react in presence of ether to get your compound this. And then to remove this magnesium 1 bromide, you always bring in acidified water, which some other students, some of your teachers could have told you dilute HCl. It also works. So you bring in acidified water and then it will take you to the compound that is required. But notice that Grignard's reaction is mostly used in synthesis reactions to increase the number of chains. Like here you are seeing that you're having 2 carbon atoms here, but here we end up with 3 carbon atoms. And it also uses as a carboxylic acid or propanoic acid, which was our main requirement. Or simply, you can combine these 2 steps by simply indicating the number. The numbers here show that this is the first reaction and this is the second reaction, or this is the first step and this is the second step. Now without the numbers, you get everything wrong. So if at all you are willing to forget these numbers, to indicate the numbers when you are condensing these steps, always go with the long route. Otherwise, you must indicate the numbers when you are involving your synthesis. So looking at another step of synthesis, we are going to be looking at hydrolysis of nitriles. Now we are saying that when nitriles are heated with dilute mineral acids, for example, HCl or sulfuric acid, or with alkalis like sodium hydroxide or potassium hydroxide, we always get carboxylic acids. For example, if you're having this nitrile or propane, since you're having 3 carbon atoms, what happens is that when you bring in acidified water and then you heat, you always get your carboxylic acid. So what this does, what acidified water does with these carbon nitriles is that it removes this nitrogen atom. After it removes that nitrogen atom, it brings in 2 oxygen atoms with OH. So that's why we just replace this nitrogen atom with OOH, and then this contributes our carboxylic compound or carboxylic acid, and this is called propanoic acid since it contains 3 carbon atoms. So going to part 4, we are saying that by hydrolysis of esters with water or base can also yield us our carboxylic acid. Now we're saying that best for lower members of the series. For example, members that do not exceed 4 carbon atoms. So here we are having a compound. Now these esterification reactions, this reaction is reversed. Usually to get these esters, we react a carboxylic acid and an ethanol. So we can also get back our carboxylic acid by condensing the ester that we formed, simply by introducing water and then we heat. Now remember that some books here, or some of your teachers might have given you warm, but warming is the same as heating, and you are advised to avoid the word warming and use heating instead, because when you are warming, you are also heating at the same time. So this compound, what this does is that it splits these compounds into two. So this one will give us methanol, and this one is going to give us our carboxylic acid. Remember that this is a condensation reaction, just like we shall be looking at it under the topic of esters. But for now, just take it as a synthesis reaction for formation of carboxylic esters. Now here I ask you for the mechanism. Leave a space so that you come back when you look at the topic of esters. Looking at the physical properties of the different carboxylic acids, we are saying that part A, aliphatic acids, as far as they don't exceed 10 carbon atoms, are going to be liquids with a pungent odor at room temperature. However, anhydrous ethanoic acid freezes at an ice-like solid below 17 degrees Celsius and has a vinegar smell. Aromatic acids are going to be crystalline solids. Now the reason why we give these physical properties is that some of you take them lightly, but just like I told you, after listing your isomers, you'll find that esters are always isomerizing with carboxylic acids. So you need to know the physical properties of either of the compounds so that you can identify the specific isomer that they are talking about. Because the next question will be describing any physical property under that compound so that you can select one out and give it as your final answer. So looking at part B, you're saying that the first 4 aliphatic acids are completely miscible with water, and you're saying that this is due to their ability to form hydrogen bonds with water. So for anything soluble in water, it must form hydrogen bonds with water. Other than that, it's going to be sparingly soluble. In chemistry, we don't have insoluble. Things are just sparingly insoluble. Now you're saying that higher homologies become progressively immiscible with water due to their greater hydrocarbon tails. That's covalence character. Now you're saying that benzoic acid is the only slightly soluble in cold water, but it's going to be readily soluble in hot water. And you're saying that now for benzoic acid, you find that this one is commonly said in practicals due to this property. It's slightly soluble in cold water, but when you warm, it's going to be soluble in warm water. And because of that reason, they like setting it in your practicals. Now you're saying that all carboxylic acids dissolve in suitable organic solvents. So looking at part C, we are saying that they have higher boiling points than alkanes of similar molecular formula, and I remember giving you a reason for such things. And you're saying that this is due to their ability to form dimers via hydrogen bonds. Remember that I told you hydrogen bonds are one of the strongest bonds in chemistry, and anything containing those bonds has to have higher melting and higher boiling points as a must. So for example, we can look at ethanoic acid. Its melting point is 60. And its boiling point is 118 degrees Celsius. While butane, its melting point is 58 and its boiling point is negative 0.5 degrees Celsius. Now let's dive into the chemical properties of the different carboxylic acids. History of the oxygen-hydrogen bond. In the carboxylic acids, you are going to be saying that carboxylic acids are weak acids compared to the mineral acids, and the reason for that is because they ionize partially in water to set up an equilibrium as follows. So carboxylic acids undergo hydrolysis in water to form the different anion, and they release protons in water. Now the protons they release in water, they react with this water molecule, and once they do so, they form what we call the hydroxonium ion. Now the equilibrium constant, which is Ka, is going to be given by the following expression. Always is always the molar concentration of the products raised to their appropriate powers divided by the molar concentration of the reactant raised to their appropriate powers. But you notice that here water is not included in this formula. The reason for that is because water exists in excess. So if it exists in excess, we don't include it in our formula. So Ka is given by this expression. Now we are saying that the bigger the Ka value, the stronger the acid. Now this is called acid ionization constant, Ka. Ka is abbreviated as acid ionization constant, and we are saying that the bigger the acid ionization constant. How is this acid ionization constant going to be bigger? It is going to be bigger when products are more than the reactants. So that means that in product side we must have something like 25, and then in the reactants we must have something like 5. So that if products are much, that means that more protons were released. So that's why we are saying that the stronger, for an acid to be stronger, its Ka value or its ionization constant value must be very high. Now you're saying that they therefore turn blue litmus paper to red because they have high Ka values. Now let's look at the effect of the substituent groups on the strength of the acid. Remember that I told you in the previous video that substituent groups, we have those ones that cause positive inductive effect and then the negative inductive effect. And you should know how each of them contributes to the acidity or to the extent of the acidity of the different compounds of carboxylic acids. Now let's look at the comparison of some of the organic acids. We're having a table showing the different formulas of the different carboxylic acids that we are having and their ionization constant values at room temperature. Room temperature is always 25 degrees Celsius, and ionization constant is always measured in moles per decimeter cubed, showing how much protons are released by each acid. Now methanoic acid is represented by this formula, ethanoic acid is represented by this formula, propanoic acid is represented by this formula, then chloroethanoic acid is represented by this formula, and then trichloroethanoic acid is also presented by this formula. Now we are saying that ionization constant for methanoic acid is going to be 1.6 exponential negative 4. The one for methanoic acid is 1.6 exponential negative 4. The one for ethanoic acid is 1.75 exponential negative 6. And it goes on decreasing up to this side, or increasing. Now let's look at the reason for that. Now we are saying that, just like I told you, you must know electron donating or compounds that have positive inductive effect, and you must know compounds that have a negative inductive effect to the different compounds, because that's the central of most of the organic explanations that are brought in word problems. You must understand positive inductive effect, you must also understand negative inductive effect. Now we are saying that the presence of an electron withdrawing group, like an hydrogen atom bonded directly to the carbon atom, which is adjacent to our carboxyl group, is going to make the carboxylic acid stronger. Now let me explain this. If you're having an electron withdrawing group, anything that causes a negative inductive effect. So let me give an example of this. So what these electron withdrawing groups do is that they withdraw electrons towards themselves. So, and this kind of withdraw, let me make it clear here. So if you're having chlorine here, attached to this carbon atom, for example in chloroethanoic acid, this chlorine atom withdraws electrons toward itself. Now this withdrawal of electrons is directed also to this bond, and also here electrons are going to be withdrawn because the electrons of these carbon atoms are being taken away from it. So it also withdraws electrons from the next neighbors. So what it does, also it proceeds in the bond between carbon and oxygen. And also it proceeds in the bond between oxygen and oxygen. Now you find that it's going to reach a point where it is now proceeding to a bond between oxygen and hydrogen. Now what happens is that electrons are going to be withdrawn away from the hydrogen atom to the oxygen atom. So oxygen is going to attain a partial negative. and then hydrogen is going to attain a partial positive. Now this partial negative is going to be large, also this partial positive is going to be large. Now once the partial positive and partial negative are large, this bond between oxygen and hydrogen becomes weak, and therefore this hydrogen ion is going to easily be released in solution. That's a simple elaboration of what you call effect of electron withdrawing groups, such as halogen atoms. So that's why you're saying that presence of an electron withdrawing group like an halogen atom bonded to a carbon atom, which is adjacent to the carboxylic group, is going to make the carboxylic acid stronger. The strength of an acid depends on how easy it releases protons in solution. So since these chlorine atoms are going to weaken these oxygen to hydrogen bonds by increasing the partial negative on oxygen and partial positive on hydrogen, they are going to cause the oxygen and hydrogen bond to be very weak. Therefore, it can easily break in solution to give very many hydrogen ions or protons, and once it releases very many protons, that acid is considered to be strong because we expect that solution to be highly acidic. Now I've seen that for this reason, chloroethanoic acid is a stronger acid than ethanoic acid, because in chloroethanoic acid there is presence of an electron withdrawing group, or a group that causes negative inductive effect. Negative inductive effect refers to the effect whereby an atom is withdrawing electrons from the main organic compound. Now let's look at the trichlor. Now you should realize that this one and this one, they both force the same effect, but here we only had one chlorine atom. That means that one chlorine atom, the negative inductive effect was less here, but here we are having 3 halogen atoms. That means that here negative inductive effect is going to be very much. Therefore we expect this one to be more strongly acidic than this one, because here we are having more electron withdrawing groups compared to this one. So we expect this one to be more acidic than this one, simply because we are having more electron withdrawing atoms, which is the chlorine atoms, compared to that in chloroethanoic acid. So that's why we are saying that trichloroethanoic acid is even a stronger acid. This is because the halogen atom has a negative inductive effect, and it withdraws electrons from the carboxyl group, reducing the electron cloud on the oxygen to hydrogen bond, and thus weakens it, which makes the acid release a hydrogen ion in solution. But this is the explanation that I gave for this chloroethanoic acid. But the reason why this one is a stronger acid compared to this one is because there's 3 chlorine atoms in this compound. Therefore, the negative inductive effect in this compound is greater than this one, and the reason remains the same. They will reduce the partial positive and partial negative. If you didn't get that reason properly, you should put it as a summary besides these notes, because it will be the one to guide you in properly understanding the positive inductive effect. Also make research about the negative inductive effect or the positive inductive effect. For positive inductive effect, we looked at it in previous video, and I told you for positive inductive effect, there we have groups that give electrons towards the main organic compound. Now, once those groups are present, for example, in ethanoic acid is the methyl group that is attached to the carboxyl group. That means that the methyl group is an electron giving group, so it donates electrons to the carboxyl group. Now once it does so, the partial negative on oxygen and partial positive on the hydrogen atom in the OH group, which is present on the carboxylic acid, is going to be very low. That means that it's going to be a weak acid, since the partial negative is low on oxygen and partial positive is low on hydrogen. The oxygen to hydrogen bond is going to be stronger, thus few protons are going to be released in solution, making the acidity of that solution to be very less, since very few protons are going to be released in such a solution. Now you're having a discussion question that you can sit down and discuss with your friends. Question 1. Chloroethanoic acid is a stronger acid compared to ethanoic acid. Here you must explain this one using negative inductive effect, and you must explain this one using positive inductive effect. And this one will take a total of a minimum of 5 marks. Now going to this question, the ionization constant of an acid of chloroethanoic acid is going to be this one, while that of ethanoic acid is this. Explain. Now this one is the same as this question in some way. They're telling you that this acidity is greater than this acidity. Explain why. Now here we are saying that acid strength decreases with presence and increases with presence. Acidic strength decreases with presence. Now here I could have said with presence of an electron donating group, for example in ethanoic acid, and increase in length of the alkyl group. Oh yeah, I think this is a very elaborative statement. I just panicked. So the statement is the acid strength is going to decrease with presence and increase in length of the alkyl group bonded to the carboxyl group. So if you look at any alkyl group, the methyl group, ethyl group, propyl groups, among others, for as long as it's an alkyl group, it's going to be an electron donating group. Now, since it's an electron donating group, the greater the number of alkyl groups present, or the greater the number of carbon atoms present in the alkyl group, the greater the positive inductive effect. And I told you, the positive inductive effect, that means that they are going to be donating electrons to the OH bond. Now, if they're donating electrons to the OH bond that is present in carboxylic acid, there is going to be a less partial negative on oxygen atom and a less partial positive on the hydrogen atom. Now, that makes the oxygen to hydrogen bond stronger, and once it becomes stronger, that means that these protons are going to be very few of them which are going to be released in solution, and such an acid is going to be said to be a weaker acid. But if you look at chloroethanoic acid, there is the chlorine atom. This chlorine atom, just like I've explained previously, it has a negative inductive effect onto the ethanoic acid, onto the carboxyl group. So it withdraws electrons. You find that it's going to increase the partial negative on oxygen atom and it's going to increase the partial positive on oxygen atom since it's withdrawing electrons from this bond. So you find that this bond is going to become weaker and it's going to be very easy for this bond to break to release many hydrogen atoms or protons in solution, making chloroethanoic acid to have a higher ionization constant compared to that of ethanoic acid. So coming back to the reason which was dotted here, we are saying that this is because there is a greater positive inductive effect in ethanoic acid with increasing number of carbon atoms that are present in our alkyl group. Now we are saying that when electrons are pushed towards the oxygen to hydrogen bond, the electron density of this bond increases. Electron density, they are talking about the partial negative and partial positive that I've been talking about, hence becomes stronger. And increased branching on the alkyl groups will also have the same effect. I hope you have summarized out something important. Now notice that here, what I wrote is far less important than what I've described in words. You make sure that you also rewind the video and you note down whatever thing that I told you in words. Now, having an assignment question here, because this is a very common question under organic chemistry and it's commonly brought back because many of you don't have the skills to interpret these questions. So looking at this question is that you are prompted that methanoic acid is a stronger acid than ethanoic acid. You explain why it's the case. So just to give you a highlight, in methanoic acid you don't have an alkyl group, you only have a hydrogen atom which is attached to the carboxyl group. But in ethanoic acid you have an alkyl group which is going to be methyl. And he said that alkyl groups exert positive inductive effect. But since in methanoic acid you don't have any alkyl group, that means that for it doesn't have any positive inductive effect. So we expect the OH bond to be weaker in this one, therefore it will easily release protons in solution compared to this one, because for it has an alkyl group which exerts a positive inductive effect, and then it will not easily release protons in solution, just like the explanations that you have been giving above. Since it's a question, you are prompted to try it out and then either consult your teacher or reach me out for guidance. Looking for question 2, we are saying that the ionization constant of methanoic acid is going to be 1.6 exponential negative 4, and we are saying that while that of ethanoic acid is going to be 1.75 exponential negative 6. You are prompted to explain the different reactions that are going to be involved with these carboxylic acids. You are going to be looking at number 1 as reaction of carboxylic acid with high reactive metals. And these high reactive metals are going to be mostly sodium, potassium, magnesium, or calcium, among others, but mostly it's going to be sodium. So we are saying that to form an organic salt and usually hydrogen gas. So whenever you're having a carboxylic acid and react it with any metal, always remember that you are going to form hydrogen gas and then a metal salt of what you are reacting it with. So what this does is that these metals, they only replace this hydrogen atom which is present on the carboxyl group only. So that's why when you're reacting it with magnesium, you are forming a magnesium ethanoate. And so is a solid giving off also hydrogen gas. You balance the two by writing appropriate measures. We are also saying that they react. Now here, balancing this, you may eliminate this one and you just put here half on as a coefficient of hydrogen. Now you're saying that they react with bases to form a salt and water. So when you're having a carboxylic acid reacting with sodium hydroxide, if you're having a base like sodium hydroxide or potassium hydroxide, still they replace this hydrogen atom, and then this hydrogen atom reacts with the hydroxyl ions, and then they form water as a whole. So we don't release hydrogen, but instead we release water. We get a salt and also release water. Similar applies, for example, if you're having ethanoic acid and react it with sodium hydroxide, you're going to get sodium ethanoate and then water. Now looking at number 3, we are saying that they react also with carbonates. Now this is the test or a confirmatory test for all carboxylic acids. Carboxylic acids are the only ones, or the most only organic compounds that react with carbonates to give us the effervescence of a colorless gas. And usually that colorless gas is carbon dioxide, whose test is to turn lime water milky or forming a white precipitate with calcium hydroxide solution. So if you're having a carboxyl salt reacting it with sodium carbonate or sodium hydrogen carbonate, you form a sodium salt. Water and carbon dioxide. For example, if you're having ethanoic acid react it with sodium carbonate, you are going to get sodium ethanoate plus water plus carbon dioxide gas. Usually in practicals, you get this one as effervescence of a colorless gas that turns lime water milky or forms a white precipitate with calcium hydroxide solution. We'll be looking at esterification reactions. Now you're saying that organic acids react with alcohols in presence of concentrated sulfuric acid, usually to form esters. For example, if you're having methanol and you react it with ethanoic acid in presence of an acidified medium, you are going to get methyl ethanoate and HCl. Now let's look at a mechanism to elaborate more on how this one is formed. Now this is a very common mechanism that is examined highly, and the common errors under this is missing out on where to put excess bonds and on where to break bonds. So pay attention to this. So usually it's a carboxylic acid induced by the acid that starts. So lone pairs of electrons on the oxygen atoms attack the proton ion. Now after attacking the proton, oxygen gets excess bonds. That's why you are seeing a positive charge on top of the oxygen atom. Now oxygen requires stability, so what it does, it breaks off one bond. Since it's more electronegative than carbon, it breaks off one bond to itself and it gets all those bonding electrons so that it can stabilize itself. But remember that carbon is going to get positively charged because its bond is being taken away, which you don't want. So what ethanol does, or methanol, lone pairs of electrons on the oxygen atoms, they come on the oxygen atom, they come and form a bond with it. Now once that bond is formed, we form a compound. We'll rearrange it like this. So this OH is the one which is here, and then this OH is the one which is here. And then the methanol we have added is this one here. Now notice that in methanol, oxygen is going to be having excess bonds since it has formed a bond with its carbon atom.
So once it has excess bonds, we put a positive charge on top of it. So oxygen will require then to stabilize. So for it to stabilize, it gets rid of one hydrogen atom, and the bond breaks to itself. So that arrow should be directed to the oxygen atom itself. And therefore, but this hydrogen is not lost, otherwise it's shifted to this hydroxyl group which is up here. And then we experience what we call a proton shift. It's always a reversible arrow. Once a proton shift occurs, this one becomes water because we added an hydrogen atom to it, and then oxygen once again is going to have excess bonds. Now this methanol that we added stabilizes, and then here oxygen will require stability again. So the bond between carbon and oxygen breaks again since oxygen is more electronegative than carbon. So it takes out the bonding electrons to itself so that it can gain stability, and it's going to be lost as water. But notice that if this bond breaks, this carbon is going to become positively charged. So we always avoid that by getting the lone pairs of electrons which are present on the hydroxyl group, and then we form a double bond. We form another bond here to replace the bond that carbon has lost so that we prevent it from getting positively charged. Now here we shall form a compound like this, but notice that when you form a new bond, here oxygen is going to have excess bonds. So that's why you give it a positive charge here. Now, since oxygen is having excess bonds, so it has to get rid of one bond so that it can stabilize itself, and it's going to get rid of the hydrogen bond. So it takes away all the bonding electrons from the hydrogen to itself so that it can stabilize itself. And then we are going to be losing a proton. So on this arrow, there could have been minus a proton. Or someone else could say proton loss, and then you end up with your methyl ethanoate. Now looking at number 5, we are saying that they also react, carboxylic acids also react with halides, for example, phosphorus pentachloride or phosphorus pentabromide, or thionyl chloride to form acid halides. For example, if you're having any salt, you react it with phosphorus pentachloride, you're going to get this halide, and then there is the corresponding hypohalide, and then it's hydrogen chloride. Now what you're forming, the halides you're forming depends on the halogen atom you're dealing with. It can either be chlorine or bromine, but not any other. But usually I encourage you to be using phosphorus pentachloride, strictly to be using this one because it's the most approved reaction without any debates. Looking at the reduction, we are saying that reduction of carboxylic acids using lithium tetrahydroaluminate in dry ether also gives us primary alcohols. So when you're having ethanoic acid, just like I talked about this reaction in the previous video, so I'm not going to re-emphasize it more here. We are just going to be reading through it. So when you're having ethanoic acid, you reduce it with either lithium aluminum tetrahydride, or you can read it as lithium tetrahydroaluminate. In dry ether, you form ethanol. It takes away one oxygen atom and then it replaces it with 2 hydrogen atoms. So that's what you should always remember. Now we are saying that, however, unlike aldehydes and ketones, they are not reduced by sodium tetrahydroborate. So do not use this one anywhere. Some of you are given fake notes by your teachers. Now looking at number 7, we are saying that carboxylic acids with beta hydrogens, that is to say hydrogens adjacent to the carboxyl group, can be substituted with chlorine when chlorine gas is passed into the hot acid, and this is done in presence of ultraviolet light. So when you're having a carboxylic acid like in this form, and then you react it with chlorine, but in presence of ultraviolet light, and then you heat it, you're going to be forming a compound of this format, and then hydrogen chloride. Now always avoid these reactions because you may only attack them when you have been provided with it in paper 1 to complete a reaction. But reactions involving ultraviolet light, try to avoid them in your synthesis as far as possible. Now you're saying that when there are more than 1 beta hydrogens, further substitution is going to occur. That means that we form a mixture of products here.
That's why ultraviolet light is not advisable in synthesis unless you are going to be forming your final product, because usually we have a lot of products being formed. So we do not encourage it to be anywhere in the middle of a mechanism. Now going to number 8, we are saying that decarboxylation reactions. And under this, we are saying that carboxylic acids are going to be heated with soda lime. Soda lime can also be a mixture of solid sodium hydroxide and solid calcium hydroxide, and then you heat. But we generally identify this as soda lime. So what soda lime does, it eliminates the carboxyl group and then it replaces it with an hydrogen atom. That's its importance. And another formula or another name for soda lime, or a formula for soda lime, is solid sodium hydroxide in calcium hydroxide. And then you heat. Or you can use this, or it can be sodium carbonate. So you're saying that when you're having solid sodium hydroxide in solid calcium hydroxide and then you heat, you're going to be forming methane. And when you're having ethanoic acid and then you heat it in excess concentrated sodium hydroxide, you're also going to be forming methane. All these reactions function to remove the carboxyl group and then they replace it with the hydrogen atom. So that means that these reactions are used in chain reduction or removal of one carbon atom in a given organic compound. So note here that although carboxylic acids contain the carbonyl group, this what we call the CO, they do not undergo any addition reaction. For example, they do not react with sodium hydrogen sulfide, or they do not undergo any condensation reactions with any of the following, with hydroxylamine, which is given by this formula, or oxime. These ones are called oximes, so they do not undergo any condensation reactions with oximes, which are characteristic of this group in aldehydes and ketones, just like we covered them in the previous video. Now we are saying that this is mainly because an orbital on the oxygen atom of the hydroxyl group. Now this reason is not relevant, but it's just for explanation purposes. Is because an orbital on the oxygen atom of the hydroxyl group, which contains the two unshared electrons in the carboxyl group, is going to interact with the p orbital of the adjacent carbon atom. Like I told you, this is not for your level. It's not going to be examined anywhere in advanced level, but it's to help those of you who want a deep understanding of what's happening in the carboxyl group of which is the main functional group in carboxylic acids. And they're saying that it's going to provide extra delocalization in the molecule as compared with that in the aldehyde or ketone, which would be lost by addition of a reagent to the carboxyl group, so that a carboxylic acid is even more resistant to addition than an aldehyde or a ketone. Now, having a question as an assignment, we are saying that unlike aldehydes and ketones, carboxylic acids do not undergo addition reactions. Explain. Now, this is a discussion question, but do not attempt it anywhere in case it reflects in the paper, although it's very rare to bring such a question. So looking at the uniqueness of methanoic acid, now we are saying that methanoic acid differs from other carboxylic acids in the following ways. One is going to be that it is always dehydrated by concentrated sulfuric acid, unlike other acids. So if you look at when you react methanoic acid with any strong oxidizing agent, for example, concentrated sulfuric acid is going to be oxidized to carbon dioxide and water. If you're using concentrated sulfuric acid, it's going to be carbon monoxide and then water. However, this is the basis of laboratory preparation of carbon monoxide, but it's a very rare reaction in organic chemistry. So looking at number 2, you're saying that on warming, now this is one of the reagents or the easiest way to differentiate methanoic acid from other carboxylic acids. So we are saying that here, on warming, it reduces Fehling's or Benedict solution to copper 1 oxide, which is a reddish brown solid, and itself is oxidized to carbon dioxide gas. Now this reaction here is possible because remember that
Fehling's or Benedict solution mainly tests for aldehydes. So it's possible with methanoic acid because it has an aldehyde group. If you look at this group here in methanoic acid, the first 3 atoms, you see that we have an hydrogen atom attached to a carbon atom, which is also attached to a carbonyl group, and which is this group here is present in aldehydes. So that's why methanoic acid has properties of aldehydes. So any reagent that tests or confounds for an aldehyde also tests for methanoic acid. However, we can differentiate aldehydes from methanoic acid using sodium carbonate, because it's only sodium carbonate that does not react with aldehydes but is going to react with methanoic acid. So when you're having methanoic acid and then you treat it with Fehling's or Benedict solution, you're going to get a reddish brown solid or a red solid of copper. And then the methanoic acid is always oxidized to carbon dioxide and water. Similar applies when you're having ammoniacal silver nitrate. Remember that I told you ammoniacal silver nitrate gives a positive test with aldehydes. And since methanoic acid has aldehyde properties, that means that it is also going to give a positive test with ammoniacal silver nitrate solution, since its properties are the same as the properties of aldehydes. Since in methanoic acid we have the aldehyde group. So you're saying that on warming, it's going to reduce ammoniacal silver nitrate solution to silver, which is going to appear as your silver mirror. When you're in practicals, silver deposits on the walls of the test tube and it appears as we call a silver mirror. And then ammonia, while it is oxidized to carbon dioxide. So you're having methanoic acid reacted with ammoniacal silver nitrate solution, but in alkaline medium. So you're going to be forming your silver mirror, which is the silver. In practicals, silver forms on walls of a test tube. That's why we call it a silver mirror. It forms on the wall of a test tube. That's why we call it a silver mirror. Now we're also saying that we form with this reagent is reduced to silver, which is a silver mirror, and then it also gives us ammonia. Now this ammonia dissolves in solution to give us an aqueous solution, but however, even if you write gaseous state, it's acceptable. And then our methanoic acid gets oxidized to carbon dioxide and water, just like you see here. Now looking at number 4, we are saying that on warming, is going to reduce acidified potassium manganate 7 solution to manganese 2 ions, and itself is going to be oxidized still to carbon dioxide and water. Now remember that I told you methanoic acid is an aldehyde, and aldehydes are oxidized by acidified potassium manganate 7 solution. The same thing applies to methanoic acid. Methanoic acid is always oxidized by acidified manganate 7 solution to form carbon dioxide and water, and then the oxidant gets reduced to manganese 2 ions. Now the reason why I gave these equations is because nowadays you are prompted to give reagents and also suggest possible equations for what you are observing. So always, as you master your observations, also master outright the individual equations on each and every topic that you encounter. 5, we also look at the warming. When you warm it with acidified potassium dichromate 6 solution, it's also going to be oxidized to carbon dioxide and water. That means that acidified dichromate 6 is always an orange solution, and then it gets reduced to its stable chrome oxidation state, which is +3, and which is exists in +3 oxidation state. Chromium exists as green, so we expect an orange solution to turn to a green solution, and then effervescence of a colorless gas always is going to be carbon dioxide, which turns lime water milky. So the equation is going to be as follows. These are redox equations. You are advised to practice them using redox reactions. You see how you can come up with the balancing using the redox knowledge that you covered in the redox reaction topic. Now we are saying that methanoic acid is able to undergo these reactions because it is easily oxidized since it contains the aldehyde group. And if you are being vigilant enough, all the reactions that we looked at above,
are the same as the reactions that are involved in aldehyde groups or in aldehyde compounds, just like we covered them in the previous video. Now you're going to be using these questions to guide you across the topical sessions or revision that you have been making. Looking at the uses of carboxylic acids, number one, ethanoic acid is going to be used in the manufacture of ethanoate. Now this is going to be required for production of polyethyl ethanoate. Now this is used in making different materials. For example, use it in office glue and then use it in wood glue, anything that is adhesive. Ethanoic acid can also be used in the manufacture of ethanoic anhydride, which are different compounds that are used by different industries, eyeglasses, and manufacture of cigarette filters. So second of all, you can also have long-chain monocarboxylic acids being used in the manufacture of soap, as we are going to be looking at this in soaps and detergents. You can also be used to make up a series of essential fatty acids, which are not produced by the body, so therefore they can be incorporated into the body directly or extrinsically. So used in food industries in production of soft drinks and food products. For example, ethanoic acid used in making vinegar. They're also used in making dyestuffs and perfumes, and also rayons, used in pharmaceutical industries, and also formation of organic acids, as in many drugs, for example, aspirin and phenacetin. Over video, you advise share the video to your friends, subscribe to the channel, and like the video so that it can be pushed to your fellow candidates. For those of you having papers, success in your exams.